In this video, we solved problem 8.2.052 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate the definite integral. Now, I know you can probably get out your scientific non-graphing calculator and get it to give you the right answer to this problem, but that's going to give you a decimal approximation. Now, unless WebAssign asks you for a decimal approximation and specifies the number of decimal places that you should estimate, if you're given trig functions and answers in radians, or excuse me, bounds in radians, you want that final answer as an exact answer. Even if you're not given trig functions, if you have an answer that has radicals in it, I would much prefer the square root of 3 to the decimal approximation to square root of 3. We want to be as precise as possible, unless we're asked otherwise, unless we're told to round. Or if we're doing an application problem, generally we want to round in that case because we don't make measurements in square roots of 3, for example. Okay, but this time we're just doing a math problem, so we want an exact answer, and we're asked to find or evaluate the integral from 0 to pi over 12 of x times the secant of 3x quantity squared. Or if you want, you could have called that the secant squared of 3x, same thing. Now, 8.2 is a section on integration by parts. So my hope is that you see this as an integration by parts problem. If not, because none of the other rules apply, hopefully you see it as an integration by parts problem because of the section that it's in. But let's think about how we would look at it if it wasn't in that section. First thing I'd ask myself is, do my basic rules apply? And they don't, because I've got a trig function squared and I also have an x here. Anytime I have a product, I'm thinking it's probably not a basic rule because we don't have any basic rules for the antiderivative of a product. So it's not that. Then the next thing we could ask ourselves was, does u substitution work? And actually you have quite a few choices for u here. You might be tempted to let u equal 3x, but the derivative of 3x is just a 3 and it wouldn't take care of that x outside. So that u substitution is probably not a good idea because that x wouldn't be taken care of. The other possibility is that since secant of 3x is all being squared, maybe u should be secant of 3x, but the derivative of secant of 3x is secant of 3x times tangent of 3x times the derivative of the inside, which is a 3, and there's no extra secant of 3x tangent of 3x out here. So the two natural choices for u don't work, so that tells me I should probably use integration by parts. Now remember how integration by parts works. In a case like this, you want to set up a 2 by 2 square. Now part of this is u and everything else is dv. The integration by parts formula is the integral of u dv equals uv minus the integral of v du. And remember, that comes from using the product rule and then anti-differentiating both sides, and we ended up with this guy after some manipulation, after some algebra. But that's our formula. So the way we apply this is we pick out u and everything else has to be dv. Now when you're choosing u, you want to choose u to be the function with the simplest derivative. Now it's not the function that has the simplest derivative to take, but it's the simplest function after you take the derivative. So usually if there is a natural log in your integrand, you want that to be your u. If there's an inverse trig function, you want that to be your u. Now those seem sort of contrary to that simplest derivative idea, but we do that for other reasons that we talk about in the videos. But if there's no log or there's no inverse trig function, usually let u be the polynomial. In this case, we've got an x. So I'm going to let u equal x, and then dv is everything else. And I'm going to write that as secant squared 3x dx. Okay, and this is a good choice for you because the derivative of x is just 1. Can't get much simpler than that. So we'll compute du by differentiating, and we'll compute v by anti-differentiating. That's how this works. In order to use this formula, we need u, v, and du. Since we've got u and dv, we differentiate to get du, so that gives us the 1 dx. We anti-differentiate this to get dv, or to get v. We differentiate here, anti-differentiate here. The antiderivative of secant squared of an angle is tangent of that angle. Now, if that was just an x, I would be done, but it's not just an x, it's a 3x. Because there is a constant inside, if I were to take the derivative of that, I'd have to multiply by that derivative of the inside. I'd multiply by a 3. But since I'm anti-differentiating, I'm doing that backwards. So rather than multiplying by 3, I divide by 3. And then, according to the integration by parts formula, the integral of u dv is u times v minus the integral of v du. So we've got 1/3 tangent of 3x times x. I'll put the x in front of the trig function. That's uv minus the integral of v times du, which is just 1/3 tangent of 3x dx. Now, at this point, you might have a rule for tangent. You might have memorized that. Excuse me. But if you didn't memorize it, it's really easy to use a substitution to evaluate this integral. And this is, so far, this is just the indefinite integral. That's what I'm doing right now. And we'll put the bounds on it in just a moment. So I'll bring out that 1/3. Now let's say I've forgotten my tangent rule. If I forget my tangent rule, that's okay, because I remember that it comes from u substitution. So I just replace tangent with whatever it is in terms of sine and cosine. And we remember from trig that tangent is sine over cosine. So tangent of 3x, keep that angle, is sine of the angle over cosine of the angle. Now looking at this, you could do u substitution twice, but let's not do that. Let's just make one substitution and choose u to be the function that includes both functions. So I'm going to choose u to be that whole denominator. That way I don't have to let u equal 3x and then let w equal cosine of u, which would make this more complicated. And the reason I'm choosing u to be the denominator is the derivative of cosine is negative sine. And then by the chain rule, we have to multiply by the derivative of the inside. Derivative of cosine of angle is negative sine of the angle times the derivative of the inside. Don't forget your dx. And I know that this will work if u equals the denominator, because that sine of 3x dx is right there. It's exactly what I want. Now, a lot of students look at this and they think, well, can't I just as easily let u equal sine? Because isn't the derivative of sine cosine? You are right that the derivative of sine is cosine, but it's a little bit misleading. That cosine is in the denominator. It's not multiplying the dx. So it's actually like a secant factor. It's a 1 over cosine factor. So letting u equal sine won't work. But if you've got a fraction like this, when in doubt, let u be the denominator. It turns out in this case that that's going to work for our u substitution. So u, or du, excuse me, is negative 3 sine of 3x dx, and I've got a sine of 3x right there. So to get sine of 3x dx by itself, I'll divide by 3 or multiply by 1/3, same thing. So our integral becomes this. I've got that 1/3 from before, and sine of 3x dx is 1/3 du, so, or negative 1/3 du. So I will say that negative times that negative makes a positive. I'll put a 1/3 there, and I'll factor the du off to the far right. And there's still an implied 1 in that numerator and a u in the denominator. One-third times 1/3 is 1/9. And the antiderivative of 1 over u is natural log of the absolute value of u plus c. and u was cosine of 3x. So maybe you remember now, the antiderivative of tangent of 3x was negative natural log of the absolute value of cosine of 3x times the 1/3. So you can have that as a rule that you've memorized if you want to, or you can just rewrite it, rewrite tangent as sine over cosine. The same works for cotangent. You just rewrite it as cosine over sine and do basically the same thing. And then I would put a plus c here. I'm going to leave off this plus c though. Well, actually, no, we'll put the plus c there for right now. That's the indefinite integral. That's the antiderivative of this function. So we compute the antiderivative. Remember, that's how the fundamental theorem works. You do that first. And then you evaluate the antiderivative at the bounds. So you remember we did that f of b minus f of a. So you take this and you plug in that upper bound of pi over 12. You take this and you plug in the upper bound of 0, or the lower bound of 0, and then you just subtract. Okay. So let's do that here. The integral from 0 to pi over 12 of x times secant squared of 3x is 1/3 of x times tangent of 3x plus 1/9 of the natural log of the absolute value of cosine of 3x. And we're evaluating this from pi over 12 to 0. And at pi over 12, we get 1/3 times pi over 12 times tangent of 3 times pi over 12. We know that that's pi over 4, plus 1/9 of natural log of the absolute value of cosine of 3 times pi over 12 again. I'll just simplify that to be pi over 4. So that's at the upper bound. And then at the lower bound, I've got 0 times tangent of 0, which is clearly 0. And then I'll have a cosine of 0 here. So I'll have 0 plus 1/9 natural log of the absolute value of cosine of 0. Okay. Now we want to simplify all of this as much as possible. The tangent of pi over, or 3 pi over 12, which is the same as pi over 4. Remember, pi over 4 is the same as 45 degrees. So that's a 45, 45, 90 triangle. And the tangent is opposite over adjacent. So kato O over A, right? So tangent of pi over 4 is 1. And then I've got cosine of pi over 4. That's 1 over square root of 2. Or maybe you're familiar with the rationalized version. If I take 1 over square root of 2 and I rationalize it, you'll recognize this. It's square root of 2 over 2. And cosine of 0 is 1. Remember, our cosine graph looks like this. It starts at the top, starts at 1. So this is what we've got here. And natural log of 1 is actually 0. So that whole piece is 0 now. So that guy's gone. So it looks like we have our answer. All this side work. Pi over 12 times 1/3 is pi over 36. And then we're adding 1/9 of the natural log of absolute value of square root of 2 over 2, which is just square root of 2 over 2. And that's one version of your answer. Or you could have written that as 1 over root 2, and it can be simplified this way. Let's see, I'll write this on the side. Log of 1 over root 2, according to our log properties, is log of 1 minus log of root 2. Because it's log of the numerator minus log of the denominator. And log of 1 is 0, so you might see it like this. And that square root is a 1/2 power, so you could bring that out front. You're like, why would I do that? I don't know. But that is another way to write that answer. This log of square root of 2 over 2 is also negative 1/2 natural log of 2. So you might see this as well. It turns out to be the same thing. I think WebAssign will take all of the equivalent forms though. just not the decimal approximation, because the decimal is not exact and we are looking for something that's exact. So either this answer or this answer will do. Let's go through that again. Okay, so we look at the original integral and we say, do I have a basic rule for that? No. Can I use u substitution? Well, no, it turns out you can't. And then we say, well, let's do integration by parts. Since there's no log and there's no inverse trig function, let u be the polynomial, let duv be everything else, differentiate to get du, antidifferentiate to get v, and then you use u times v minus the integral of v times du. Evaluate this integral. If you know the basic rule, it's pretty simple. If you don't know the basic rule, just rewrite it and use the u sub. And then you're able to get the antiderivative. Now you can bring the bounds with you the whole time. So we could say this from 0 to pi over 12, this from 0 to pi over 12. You technically have to change the bounds here. We need bounds for u. But eventually we get this answer evaluated from 0 to pi over 12, which is what we had on this sheet over here. So then you just plug pi over 12 into that function and simplify. And you substitute x equals 0 into that function and simplify. And you get this. And that's the exact answer.